Lesson 60 is the first of 3 lessons on a subject called the solids of revolution, and there's different methods for finding volumes using integrals, and this is called the disk method that we're going to be looking at here. And you've got some new rules. You've got to think about taking a volume and breaking that up into discrete areas of area A times a thickness dx. And so one of those formulas is the integral of from a to b of a of x dx. So, and that would be like if your y-axis is an area and your x-axis is x. So area with respect to x. You find the area under that curve, which sounds kind of weird. You find the area under an area curve, that gives you the volume. It does. It makes more sense if you understand what integrals are, right? And that whole process that we went through, and you've got a bunch of lessons that it builds off of a lot of previous concepts, and they all connect to one simple idea learned in lesson 19 on an xy axis. If y equals f of x, then as delta x becomes an infinitesimal dx, we can use integrals to find the integral of f of x dx. You've done problems where if f of x is a velocity, like a meters per second, and an x is a time in seconds, then f of x times dx equals distance over time times time is distance. You know that if f of x is an acceleration and x is time, then integral of f of x dx is velocity. So all we're doing here is this. In lesson 60, we're just saying that if f of x is an area and x is position, then integral of f of x dx is a volume. Integral of a to the x dx. We've got a couple other formulas that are connected to that as well. You have a volume of a function, and you think of its height, its f of x value, as a radius, and you revolve that around an x-axis. You end up with a volume like that. It would be the integral of from a to b over some x interval a to b of pi r squared, where r is a function output times dx. And just think about that. If you rotate that around the x-axis, it's going to be a circle with a specific area. Then you times it by a thickness dx. You've got a little disk with a height dx. And so in other words, integral from a to b of pi f of x, instead of radius, f of x squared dx. You can do the same thing, rotate it around the y-axis, so those would be in terms of dy instead. And those, though, they usually have a radius that's x long, right? And so that'd be like an integral from a to b of pi x squared dy. So you'll see all of this here a little bit better in just a minute. But if f of x is an area and x is a position, then f of x dx equals a volume. That's our general form. That's what we're saying there. And we can also think of it as a radius, and so it would be a pi r squared. We can make a little circle. So I'm going to be going back and forth from just the general form a of x dx to the solid of revolution form, kind of going back and forth a little bit with those two right now. But look at this. This is a real-world example of solids of revolution and how they actually, to make a part with this 3D printing technology. It's shown at the top of your reading assignment, company Impossible Objects, making these carbon fiber sheets. And so each one of those, I mean, just imagine each one of those is going to have a thickness to it, dx, right, or delta x. And then they put some inkjet material, liquid material on there, then a layer of polymer powder that sticks to the wet fluid, and they remove the dry powder there in step 4. And you can see that little area, this area that I'm highlighting now. So for a particular layer, a particular dx amount. And then they go to the next layer, and the next layer, and the next layer, and they layer it all up. They stack all those sheets, compress them, heat them, and then use a high pressure hose basically to remove the excess material that didn't have that liquid and the powder applied to it and stuck to it, and you get a solid part. Isn't that interesting? And think about it, for the people who made this machine to do this, they had to think continuous object broken up into discrete pieces. They had to think of that continuity and discreteness, that calculus fundamental, in order to do that and make a real-world application with it. And we know that computers, they can't do infinitesimals, right? They can't do dx, but they can do delta x. And the smaller on machines like this, as technology advances, they'll be getting thinner and thinner layers, right? They'll be making delta x smaller and smaller, and that'll give them better resolution. When you hear that word resolution in technology, a lot of times that means, if they say we improved our resolution, that means they made delta x even smaller. Machines, computers, they can do delta x. They can't do dx, but with calculus we can do dx on our paper and with a graphing calculator, things like that. So starting in that f of x delta x form, though, looking at those layers by layer, that's the best way to think about the solids of revolution concept, including solids of revolution and the disk method. So that method allows us to calculate an exact volume from a curve revolved around either an x or y axis. So beginning here, let's just start. Make an xy axis on your paper and sketch some sort of curve, maybe something like that. And we'll say that that's over the interval from A to B. Okay? Now let's revolve that around the x-axis to create a volume that has that pattern to it. So what we want to do there to do that is, let's just do that discretely, delta x by delta x right now. And so what we'll do is just right here at the end, we'll just make a little cylinder, or not a cylinder, a circle. Then it'll turn into like a little mini cylinder. We'll make it delta x thick. So it's like a little mini cylinder of thickness delta x. And so that little volume that we just made, delta V, is equal to pi times f of x, which is the radius at that spot, pi times f of x squared, pi r squared. We're thinking of the function at that b, at b as a radius, f of x squared times delta x. So we have a little mini disk or cylinder there. Now, do it again. Right here. And do it again right there. And so on all the way down. We're going to end up with a volume coming around like that, right? We sum all of those f of x squared times pi times delta x disks together. As delta x approaches an infinitesimal, we end up with integral of, I'll put pi on the outside, f of x quantity squared dx from A to B. We can get an exact volume that way. Look, here's a similar curve. It's in Onshape, the CAD program that in the first quarter I encourage you to learn a little bit about. And what we can do here is just kind of finish this out. We have to have a face. We have to have an area under that curve. It's a little bit different method, but just think about that solid of revolution there. So I can use this line tool and go from here and go straight down. Click. I made that segment, then go from here to the origin there. And make a line there. Hit escape. Now I have that surface there. I can click on this Revolve tool, and I can click on that face right there. And so I'm doing face of sketch 1, and then notice how it has there in red revolve axis. So I click there, I select the x-axis. I want to revolve it around that. I'm done. Look, it immediately made a volume for me. And there it is. We can see that solid of revolution. It didn't use the disk method there, right? But that idea, though, we revolved that function around the x-axis. Let's go ahead and do a few examples now and start with a simple one, just a line pattern. Find the volume of that solid rotated or formed by rotating y equals minus x plus 2 about the x-axis. So we see the function there on the left. We see the volume that's formed by rotating about the x-axis. So just rotating about that axis. Just think about that pattern, rotating it around. You'd start here with a bigger circle, right? With a thickness to it, one disk, then another one, then another one, then another one, and so on. And as delta x approaches dx, the infinitesimal, you get your most accurate answer, and that's how we do the integral, right? So we know that we want to revolve this around the x-axis. So we're in lesson 60, apply our volume formula, integral from a to b. And it's a good idea to write this down first. That helps you memorize it, and it also is your template to help you think about what do I need to do next. Integral of f of x squared, make sure and square that, times dx. So what's our interval here? Well, look at that graph. It's from 0 to 2, right? That's where we're going here with that. And so that'll be integral 0 to 2, and we could put the pi as a factor out there, right? Because that's a number. And then f of x, what is that equal to? Well, it's minus x plus 2, right? So we have minus x plus 2 squared times dx. So expand that, pi, integral from 0 to 2 of x squared minus 4x plus 4 dx. So that's going to be equal to pi x cubed over 3 minus 4x squared over 2 would be a minus 2x squared plus 4x on that interval from 0 to 2. Now, you could solve that on a graphing calculator, right? In fact, you could just put that right there, figure that out on your graphing calculator and get an exact answer. So in your practice sets, a lot of times this is where you're going to stop, is right there. And that's going to be your answer. You keep going with this just to see how it all is going to work. Pi times 2 cubed over 3, that'd be an 8/3. And then minus 2 times 2 squared, that'd be a 8. And then plus 4 times 2 is a plus 8. So those 8's cancel, and we're left with 8 pi over 3. We weren't given any units or anything, so we could just say like units cubed. So you didn't have to do that part, but if you did what I have highlighted in green, if you did that on a graphing calculator, just parentheses minus x plus 2 squared times pi, do that on your graphing calculator, find the area under the curve, you're going to get 8 pi over 3 for the result. Now, the observant student's going to notice that that's the volume of a cone with a height of 2, right? It's just this, pi r squared h, 1/3 of that. This should give us the same result, right? This is another reason that we want to do that answer highlighted in red, because it's kind of easy. I mean, it's you could just use this formula, 1/3 times pi times the base radius there is 2 squared times a height of 2. So the height is from here to here, right? It's kind of the cone's laying on its side. But again, we're going to get 8 pi over 3, right? So another way to check your work on a cone result like this, when the edge is a line. Let's move on now to problem 2, though. Find the volume of the solid form by rotating about the x-axis, the region bounded above by the circle whose equation is x squared plus y squared equals 4, and then bounded below by the x-axis. Note the resulting volume is a sphere, so what we're really doing here is 4/3 pi r cubed. So that's too easy, though. That's not really applying the integral formulas here for this. But think about what we're doing here. The region bounded above by the circle. So bounded above by that circle, and then revolving that about the x-axis. So starting over here on the left, we'd have like basically no disk, and then a little bit bigger one, a little bit bigger one, a little bit bigger one, and so on and so on and so on, summing all of those up. So what are we wanting to do? We're wanting to do that integral from a to b of pi times f of x squared. So, and of course times dx. Now, y is what f of x equals, right? Rearrange the circle equation. Y squared is equal to 4 minus x squared. That's saying f of x, quantity squared, is equal to 4 minus x squared. So we know what f of x squared is already. And so we can just say integral from a to b. So we're going from minus 2 on the left, right? Minus 1, 2 over there to plus 1, 2. Going from left to right there, minus 2 to plus 2 of, put the pi on the outside there, and then it's just going to be 4, parentheses 4 minus x squared dx. So that is equal to pi, parentheses, integral of 4 is 4x, x squared, that would be a minus x cubed over 3 on that interval minus 2 to 2. And so on practice sets, that's probably where we would stop, is right there. If you wanted to keep going, you could. You'd end up with 32 pi over 3 units cubed, if you wanted to put some units on that. Units cubed. There weren't any like meters or inches given, but you could say units cubed. 32 pi over 3. I mean, think about it. 4/3 pi cubed is the formula for the volume of a sphere. It should be the same, right? 4/3 pi times 2 cubed. 4/3 pi times 8. That's 32 pi over 3. Let's do one more. This time we'll revolve it around the y-axis. So you can see that solid form there, and let's just read this through. And it says we can use a graphing calculator. That's what the GC is there for. Find the volume of the right solid generated when the region bounded by the y-axis, and the function y equals 2x, and the line y equals 5. We need to know, how tall it's going to be, so we have to have a stopping point there when that is rotated about the y-axis. First off, always do this on these volume problems. Write that, use that as your template. V is equal to the integral from a to b of pi, parentheses x squared dy. Okay, we want to put x, that's our radius here, right? So think about the disks, what those would look like. Little disks like this, getting a little bigger there, and so on all the way up to there, revolving that around the y-axis. That radius from there to there, that's equal to x, right? So think about this. If y is equal to 2 to the x, we want to have pi y something in there times dy, right? So we want to rearrange this and get our function y equals 2 to the x in terms of x equals. So how do we do that on a problem like that? Go way back to lesson 5 and think about taking the logarithm. We'll do the natural logarithm of both sides. Natural log of y is equal to natural log 2 to the x. So that allows us to apply the power rule, right? Natural log of y is equal to x natural log 2. Therefore, x is equal to natural log y over natural log 2. So we're doing this on the interval. I mean, you can see it on the graph here. It's from 1 to 5, right? So this is 2 to the 0, right? That's when x is equal to 0. Anything to the power of 0 equals 1. So it's from 1 to 5. Write this out. All we need to do is get our integral set up here from 1 to 5 of pi times natural log y over natural log 2, parentheses squared dy. That looks kind of complicated, but we're using a graphing calculator on this, right? So there's a pi button on the calculator. We'll just press that, and then times parentheses, and we'll hit the natural log button here. Natural log of, we can't say y, we have to think of it as x on the graphing calculator. Even though we're revolving this around the y-axis, we just say log x on here. The calculator doesn't know what we're doing. And then divided by, and then we'll do natural log of 2. And so you have to hit that control e to the x to get the natural log on there. And then on the outside of that, we raise that to the second power squared. Hit enter. There's our graph. And now we want to integrate that. So we go to Analyze Graph, Integral, lower bound, type in a 1, enter, and then we move over so that we start seeing that shaded area. Our upper bound is 5, hit 5, enter, and there's our area, 31.8. We could change the size here a little bit if we wanted as well, just so we can kind of see the whole graph there, the whole shaded region. We shaded an area, but because y is in terms of an area, it's area times x is a volume. And so that is equal to 31.8 units cubed. And there's our answer. And that is all for lesson 60.